Alrighty, welcome back everyone. Today we're doing what's called numerical integration. So up to this point, we've done, the first thing we did was to find area under a curve was to do infinite amount of rectangles, which I kind of told you we'll probably never ever do again. And then we talked about Riemann sums and how Riemann could break it up however you wanted to. Those are all good methods. They're a little more time consuming though. So some mathematicians after that tried to come up with a way to be a little more consistent. If you can't find the area by using a picture, or you can't find the area by the ways we're going to show you later, there needs to be another way to estimate this. So this is called numerical integration. It's finding the area under a curve by drawing rectangles, basically. So it's going to feel a little bit like what we've already done, but it's more specific and more pointed. And these are the ones you need to know. These are the ones that show up on the AP test all the time. So if you have, a curve from A to B and you just break it up, this time we're going to break it up into a certain amount of rectangles. So in this case, let's color this a little bit, endpoint. So rectangle 1, rectangle 2, rectangle 3, rectangle 4. So let's say we want to break this area from A to B up into 5 rectangles. We would predetermine the number of rectangles to do. They would always tell you. And then there are 5 rules you're going to learn today to how to find this area. And they're all estimates. Some are better than others that you'll see. The first things first is we want the rectangles must have the same width again. So in this case, our delta x would be the width of that rectangle, would just be the length of the interval divided by how many rectangles you have, right? So the 3 first ones are called the rectangle rules, and it's basically just kind of like inscribed and circumscribed. But remember the inscribed and circumscribed, I said they only worked to all be inscribed or all be circumscribed if the graph was always decreasing or always increasing. So you notice this curve up and down, you can't call them inscribed and circumscribed. So we just call the rectangle rules are very simple. LN stands for the left rectangle rule. All this means is you use all the left-hand edges to find the heights of the rectangles, right? So let's just say these all had, let's just say these all had width of 2 or something like that. They're all going to have the same width. To find the left-hand rectangle, to use the left-hand rectangle, you just find the heights by using all of the left-hand edges. You just plug the left-hand numbers in, whatever they are. Very simple. I'm not even going to do an example. The right-hand rectangle rule just means plug in all of the right-hand endpoints to find your heights. If it was always inscribed or always circumscribed, the left and right would be the same, right? So if you had a curve that's always decreasing, notice we go from here to here, and we use the left-hand edges. They're always circumscribed, right? And if I use the right-hand edges, they'd always be inscribed. If it was increasing, it'd be just the opposite. But we're not going to concern ourselves with that. We're just always going to use the left or always use the right. The third method is called the midpoint rule. And that just means go to the midpoint of the rectangle and use that to find your height. We just stay consistent with each rectangle. Notice we have 5 rectangles to add up. We just stay consistent. Either always use the left, always use the right, or always use the midpoints, okay? So those are the first 3. These are not the 3 we typically do because they're not as good as the other ones. The fourth one is called the trapezoidal rule. So I'm going to give you a formula for the trapezoidal rule, but I'm going to say just ignore the formula. People want to memorize this formula for some reason, but don't. And here's why. You can see the formula is kind of complicated. The real thing you want to know is the trapezoidal rule is simply the average of the left and the rights. You can try to memorize this formula. I'm not even going to show you this formula. I could show you why it works, and the left hands and the right hands, and there's 2 is the average, and yada, yada, yada. But for me, it's a waste of time and a waste of memory. Just remember that the trapezoidal rule says find the left, find the right, and find the average of those 2. That's called the trapezoidal rule. It's going to give you a little bit of average most of the time. And then the last rule is called Simpson's rule. Simpson came along and said, hey, I got a better way. I'm going to tell you the same thing about the formula. Don't memorize the formula. It's got x sub 1/2 because it's got midpoints on this one. So those 1/2 are like midpoints. Again, just remember how he determined it is very simple, actually. Simpson's rule is a weighted average. It takes the midpoint rule and the trapezoidal rule. It takes 2 of the midpoint rules, actually, adds it with the trapezoidal rule, and divides it by 3. It's a weighted average of the two. It turns out to be a better approximation. Typically on the AP test or my test, I'd probably ask the trapezoidal rule, the Simpsons rule. Simpsons rule is a great rule because notice Simpsons rule in order to do it. You got to use the trapezoidal rule right here, which is the left and the right, and you got to use the midpoint, right? So you got to know all 3 of those anyway to do Simpsons rule. The trapezoidal rule only needs left and the right. So you're going to get probably more of those. So it turns out that mathematicians have been able to prove how good these approximations can be. And it turns out the reason it's showing up right here also is because it's dictated by the derivatives, believe it or not. So these are called error estimates. I'm going to just tell you to take a picture of this. I'll probably try to send it to you. I'll probably hopefully remember, but you don't have to memorize this for sure. This would always be given to you in a problem. On the test, I would probably just give you this sheet or the midterm. If it were an AP test, they'd just give you the problem. So what this is an error estimate for the actual area. So I is the actual area. By the way, I'm not going to do an example. I think there might be an example in the book. They're really just straight applications of those formulas, okay? So I is the actual area. What this says is the absolute value of I minus ln, or the left-hand rectangle rule, is the how far apart are they? Okay, remember, we're never going to know the real integral, and it's actually, it's not how far apart, it's at most less than or equal to. Notice it doesn't say equal. So this would be like the biggest the error would possibly be. So the biggest the error can possibly be for the left-hand rectangle rule is b minus a squared over 2n times this number k1. I'll talk about what that k1 is in just a second. For the right-hand rectangle rule, it's the same. For the midpoint rule, it gets a little smaller. So it's actually b minus a to the third over 24n squared times k2. And again, I'll talk about what the k's are in just a second. The trapezoidal rule, k2 also, b minus a cubed over 12n squared. And Simpson's rule, notice is the best one, the smallest one, is b minus a to the fifth over 2,880 n to the fourth. A lot of proof there. We're not going to do that times k4. So what are those k's? Well, they turn out to be derivatives. So k1 is the largest value the first derivative can ever be on the integral that we're dealing with. So what we would have to do is take the derivative, okay, of the function and then figure out the largest value. So find critical points maybe. Typically, they're pretty easy. It's always easy to find the largest value. And typically, the largest value is always on one of the endpoints, just to make our life easier. In a real world, that wouldn't be the case, but we don't want you to be taking derivatives and finding minimums and maximums and doing all that work. So typically, they'll be on the endpoint. It's possible it could be on in the middle, but typically on that point. And then K2 would be the second derivative. K3, third derivative, which we don't use. K4th, so second derivative. Third and fourth. Okay. What this gives you is an error estimate, right? It doesn't tell you the actual error, because if it told you the actual error, we would then know the real area, which means we would have known that first place. We can't do that way. This just tells you how big the error can possibly be. So when I ask the question, I'll kind of say something like, what's the biggest the error can possibly be? The advantage to this is you can actually, before a problem starts, figure out how many rectangles to use to get it within a certain area. So here's a little example problem. So basically, up till this point, the problems are going to give you a function. They're going to give you an interval, and say estimate the area, and they'll say use the midpoint rule with 4 rectangles, and then they'll say error estimate. It's just all a matter of plugging right into the formula. I'm not going to give you an example here. You can look in the book for an example. I'm hoping you don't need an example. You should be able to just plug in numbers. So what you would do is graph this thing, some sort of cubic from 0 to 4. 4 rectangles, so it'd be 1, 2, 3, 4. So 1, 2, 4 rectangles. And if I wanted to use the midpoint rule, I plug in a half, plug in 1.5, plug in 2.5, plug in 3.5 to the function. Calculator's okay. And then multiply them all by the widths of the rectangles. Widths in the rectangle are all the same in this case. You can factor that, would just be 1 in this case. If you want to do a Simpson rule, you do averages, that sort of thing. And then the error estimate, you just plug in. So if we're doing a midpoint rule, you'd go b minus a to the third over 24n squared. You'd take the second derivative, which would be 9x squared plus 2 would be 18x. The biggest that derivative can be, 18x on 0 to 1, it's just 18, right? Or sorry, 0 to 4, 0 to 4. So it's 72. So you plug 72 into your error estimate. So the nice thing about the error estimates is you can actually predetermine before you start how many rectangles to use based on a method in order to get within a certain range. So I got this little problem here. We got this graph of 1 over x, which looks like this. We're going from 1 to 3. We don't know how many rectangles, but we want to get it within 0.001 using the trapezoidal rule. So what we do is we use that trapezoidal rule formula for the error estimate with a 0.001 and solve that equation for n, for the number of rectangles. And then I'll know how many rectangles I have to use to get within 0.01. Remember, never exact. The error is never exact. It's just the biggest. So there's the formula for the trapezoidal rule. The actual integral minus the trapezoidal rule. The important thing is that it's k2 times b minus a cubed over 12n squared. Whoops, I jumped some steps here. Sorry, I'll show you what I just did. So I plugged that 0.001 into my error. And then what I did was, since this used the second derivative, which you're going to see me over here, the function is actually x to the negative 1. So this is f. F prime is negative x to the negative 2. F double prime is 2x to the negative third, or 2 over x cubed. We're on the integral from 1 to 3. I want to make this as big as I possibly can. And again, like I said, usually the answer is an endpoint, okay? So try those first. You can see that this function, the smaller x gets, the bigger that number gets, right? So we just want the smallest number, so it's 1. So at x equals 1, we get 2. That's that 2 right there. That's the k2. B minus a to the third power. 3 minus 1 is 2 to the third power over 12n squared. So we just got to solve this equation for n. It's pretty straightforward at this point. 12n squared equals 16 over 0.001. I brought the 12n squared. I just switched the 12n squared with the 0.01 just for algebraic purposes. N squared. And typically I would do this actually, believe it or not, just with an equal sign and then just remember afterwards. It gets a little confusing with a less than or greater than, but I wouldn't worry too much about it. So n squared equals 16 over 0.001 times 12. N squared is 1,333.33. Take the square root of that, you get 36.51. We want to get within 0.001. If we use 36, we're not going to make it. So it's not about rounding. It's just always you got to go to the next amount of rectangles. So we would need 37 rectangles. Don't worry, I'll never make you do a problem with 37 rectangles. It would take forever. But this is a nice little showing you that you can predetermine, hey, I want to get really close. So even if you only wanted to get within one of the area, maybe it wouldn't be such a big deal, right? In terms of how many rectangles. So that's numerical integration. It's a pretty important tool, and it's for sure one of the few things I can say. I know there's always problems like this on the AP test, usually 2, 1 in the multiple choice and 1 in the written. So we'll practice them quite a bit in the homework tonight, plus in class the next day. But numerical integration is just a method for finding the area using a certain amount of rectangles and always using the same edge of that rectangle to find the height of the rectangle. So that's it for this one. I'll see you on the next one.